Okay. But they're easy ones. Let's get started. Good to see you all. Hope you had a good holiday. A couple things before we get started. One is, this is the last lecture for this course. We're not going to have one on Thursday. Just canceling it so that you have a little more time to work on your final project. And really, we've come to the end of the content plan for this course, which is great. We'll do our second day of reinforcement learning and cover a few more topics in that, and that'll be that. So there's that. Thanks for getting homework 4 turned in. Most everybody got it turned in on time, so great job. Hopefully having a little time over the holiday helped for that. Any questions? Any questions going into it?
So this is the last lecture. There's no lectures next week?
Right. Yeah, I mean, already here in the finals week next week.
It's not technically finals.
Yeah, that's the week after.
Yeah, but I mean, you're getting, I don't know, like you're getting somewhere into it. Yeah. What's that?
But for this class, we are treating it like.
Yeah, that's right.
But today is the last day.
That's right. That's right. So you can have this time to work on your final projects. Usually, it helps most people. Some people actually have their final project turned in. So those people can do what they want at the time. But for a lot of you, it will help to have the extra time to do the final project. Yeah. So good question. What else?
You're going to make an announcement about that, right?
You're going to go on Canvas?
Yeah. Yeah, because it's kind of big.
Yeah. Other questions? Any questions about homeworks or final projects? Okay. Sounds good. All right. So let's get going here. So reinforcement learning. So you remember from last time, we kind of set up the problem and we went through a whole lot of formulas that had R's in them, R's and gammas. Remember that? Been a while, been a week. But we set this all within the framework of Markov decision processes. So remember how this was set up. There were these, we had the states of the environments that we were in, the actions that you could take from within that environment, given whatever state you're in. And really, the whole thing that we were trying to, the whole way that we frame this problem is that we were trying to learn what we call a policy. So a way of determining what action we would take given the state that we were in. And our objective in this was to find some kind of optimal policy for doing that. Okay? And the way we defined optimal was that it maximized this thing that we call the cumulative discount, or the expected cumulative discounted reward. Right? So we had this notion of a reward. You get rewarded by taking certain actions in the state or in your environment, given the state, and there's really a policy will kind of generate a trajectory of these things. It could do that stochastically, meaning that there was there's some there's some probability of taking one action or another, not necessarily having to be deterministic. So this idea of being the expectation of these rewards, these trajectories of rewards over over all of the choices that you could make within that environment. We want to do an expectation over all of that, discounted, meaning the rewards way off in the future are going to be discounted more than rewards that are given near. meaning that those rewards we have in the future can have an effect, but it'll have far less effect than rewards that will come sooner in that trajectory. And anyways, we want to maximize. We want to find a policy that maximizes that. So given that setup, we defined a number of functions. We defined a value function that told us basically like the value of a state within the environment, given a policy. We defined a Q-value function that was like a state and an action, or sorry, the value of a state and an action, given a policy. And that there was this notion of an optimal Q-value, where where you would get you're maximizing again this cumulative discounted reward given the state and the initial state and initial action. But now this is maximized over all possible policies. All right, so like all ways of making decisions about what action you would take next, that's like the optimal Q value. And then we made this, we defined this what's known as the Bellman equation. We sort of gave you some intuition about why this recursive formula for the optimal Q value should be what it is. This is the idea of being something like optimal Q values are still optimal after you take an optimal step and maximize over the possible actions from the previous action, from that previous state. So and this kind of motivated some of the mathematical formulation for what we're trying to maximize, like the fact that we had this geometric series in this discounted factor and so forth. So anyways, we had this Bellman equation, and we use that Bellman equation to actually set up a kind of learning algorithm. Whenever we have a recursive formula like this, and like the function or the functional on the right-hand side here of our function, our optimal Q value function, has a certain contractive property. Basically, it's like mapping space back into itself. Then there's a nice mathematical property that says that if we iterate these values, if we take an initial value and use that to give us the next value and so forth, that sequence of functions actually will converge to this optimal key value function. And that's something called a contraction mapping theorem. But in general, this is how we approach this problem. And however, we don't necessarily just solve this directly. What we do is we estimate, but this is quite complicated. There's a lot of possible states and actions. What we do is we now say, okay, well, this is parameterized as a neural network. This neural network has, a certain set of parameters. And what we do is we say, all right, let's optimize. Now, the problem setup is let's make the left-hand side the right-hand side. We want to find the parameters such that whatever the Q of those parameters on the right-hand side equals the Q of those parameters on the left-hand side. And that's what the setup here is. Basically, this Y is our right-hand side. And now we have we take the square of that because we want a loss function that we're going to minimize. And so we can set that up. And so our backward pass now to do this just looks like basically taking a gradient of that loss and doing this update. Now there is still a kind of an iterative idea here because of the recursive nature of this. So there's still previous parameters from the previous iteration and the current parameters that we are learning. But still, the idea here is that we have a well-defined loss and and we're simply doing, as we've done all semester long, doing gradient descent. Okay, questions just on that review? Do we recall enough of this to keep going? So it's a lot of math and kind of pushing symbols around, but the idea here is that we're trying to learn this optimal Q value function. And again, the reason for doing that is that we can use the optimal Q value function to give us the optimal policy. Basically, the optimal policy is whatever state we're in, find the action that gives us the highest Q value from the optimal Q value function. Okay, so what does this look like in practice? So a nice setting where this has been done a lot is in playing Atari games. So you've probably seen some of this if you've been paying attention to the news in deep learning over the years. But Atari Games became this really interesting playground for reinforcement learning, mainly because the rules were simple and well defined. There's a lot of these games, there's dozens and dozens, and the action space is quite simple. The controllers for an Atari game are actually quite simple, and so and this is not just checkers or backgammon, things that have been done in the past. Even chess. This is something quite a bit different with a lot of variety, especially in terms of the state space, where state spaces are these interesting arrangements of pixels, right? So yeah, and then of course rewards are well defined as well. The scores for these games, the score, however the scoring is done for each game, is an appropriate reward to use in these kinds of settings. So how do we do this kind of thing? Well, we need a Q value function that's parameterized as a neural network. So what does this look like? One approach that was done early on that worked quite well is to do something like the following. Your state would be something like, in this case, the last 4 frames of a game, right? So all of these games are being played forward in time. So you might want your state to be a little bit more than just the current frame, to maybe give you some kind of notion of what's happened in the past. That would be, these kinds of things are hyperparameters for the setup of the network. This particular setup is using something like the last 4 frames. Notice that the state is defined as 84 by 84, assuming this is a set of square, a square image, and you'd expect it to be 3 channels, right, because of the colors. But often, what's been being done here is to convert it to grayscale, to do some kind of downsampling, since you don't need to have exactly every single pixel as defined here, and often cropped to maybe this kind of to this appropriate size, or resized in some way. So, anyways, defining your state in some way similar to this. And then what are you trying to do? Well, you're trying to learn a Q value function, which is to give you a value for your state and your action. So this is your state right here. So you need to be able to have an action as well, to provide a value for the action. So the way that these networks are set up is to basically have a convolutional network that processes this state and then turns that into values, one for each of the actions. And in most of these games, the action space is quite simple. You can move left, right, up, down, right? Like a simple joystick, left, right, up, down. So there's 4 actions, so you need a Q value function, you know, with some state S needs to provide values for 4 different actions. And so what this network is going to learn to do is provide that value, that score, for 4 different actions. So what you can see here is that there's, you know, this is actually quite simple. A simple set of convolutional layers. There's 8 by 8 convolution here. This is actually, you know, this is quite old. We probably wouldn't use these sizes here, but they were used back then. You know, actually small numbers of filters, large strides for these large filter sizes. And then quickly collapsing down to a fully connected layer, and then another fully connected layer to give you the right size. So this was of length 256, and this is of length 4 here. And that's what you're going to learn. That's what you're going to learn here. This is the network that's parameterized, and that's what's going to go into this kind of iterative loss function. Yeah.
I might be wrong, but this is only for discrete action, right?
Mm-hmm.
But is it possible to extend this to a continuous case?
Yeah, you could. You would have, basically the loss is the thing that would change there, right? So you would have, in the continuous case, you'd have more like a regression loss. So something would look more like depending on the setting, but something would look like a mean squared error. But typically what would be done, even in like the case where there's like what appears to be a continuous action, you would usually just discretize that and still do what would appear to be like more like a classification type problem, because those just tend to be better. They're easier to train and give you better precision on the final loss.
So what's the activation? Is it ReLU, and then?
Yeah, always ReLU.
And then what's at the top? Is there a loss function? Is it cross entropy or?
Well, no, the loss function.
Oh, it's the Q.
Is that crazy iterative Q loss, exactly.
Is that in PyTorch? Is there like a big Q?
Mm-hmm. Yeah. I mean, there's all kinds of nice libraries for these kinds of things. And this, I'm kind of giving you like the foundational things. And there's lots of. I mean, we're looking at a couple of different ways of doing reinforcement learning that are Q value learning today. And then there's lots of variations on these things. Okay, our input state, our familiar convolutional layers and fully connected layers, and then our 4D output for all the 4 different kinds of actions given the state. And yeah, the number of actions kind of depends on what game you're playing. This is something simple with left, right, up, down. So what's good about this? A single forward pass to compute the Q values for all actions, right? So like once this thing is trained, because the action space is small, it's actually quite efficient to go from your state to to computing all of the Q values, and then picking, of course, like the one giving the highest value, and that therefore generating your optimal policy. Seems almost too simple, right? Like, I mean, yeah, sorry, just real quick. Like, this actually works quite well for these simple Atari games. This kind of neural network. And, all of the like powers in that loss that we generate from the Bellman equation. So, I mean, I don't know. I always feel a little bit surprised when I do this slide, just to remember that it doesn't require a whole lot of understanding the state that the game is in order to learn a powerful and effective Q value function.
So for the Q values, has anyone tried to calculate the true Q value and compared it to this? Because isn't this just an approximation of the true Q values?
Yeah, absolutely. Let's see. I'm trying to think if I can think of any thing off the top of my head. In these simple settings, you can imagine doing something like that. The problem, of course. Actually, okay. So let me step back. You can do this. You can do this actually quite well for games where the state space is also very simple. Notice here that actually the state space is actually quite complicated, even though it really isn't. Like there's a lot of pixels here, but really, like the actual meaningful parts of the state are easier to kind of just describe like in lower dimensional way, so to speak. But you'd have a hard time like enumerating all of these things by hand, right? Just like combinatorially, this would kind of explode. So this is actually one of the powers of neural networks, right? Is it learns to, generalize across similar state spaces that it hasn't actually seen necessarily in playing all these games. So
you can like effectively play Atari games with just like under 500 brain cells.
I guess it didn't seem like that when I was a kid, but yeah.
Is it possible and or useful to include some of that richer information into the input? Because like there's a lot of like non-machine learning programs you use to like classify those like richer objects that we know exist in the game.
Yeah. Yeah, definitely. I mean, there's no like everything that we're doing here. There's nothing that says like it strictly has to be just this neural network, right? The point is that like just this simple neural network though works quite well. But yeah, like the intuition you have there is right. Like if there's other kinds of like if you have easy to compute other ways of determining the state, you can use that information to describe your state, right? It doesn't have to be these 4 frames, right? It could be some pre-processing of those frames into like a lower dimensional description. And if that's a good description, then your Q value function should be easier to learn and should be probably more accurate.
This looks like it'd be, so this is done with a feed forward, but this looks like this should be done with maybe like a LSTM maybe?
No. I mean, because we in this case, because we go to grayscale, this is like literally the input tensor is 84 by 84 by 4. So this looks a lot like what we've done before, just a 3-way tensor. But instead of there being 4 channels, or 3 channels RGB, there's 4 channels. Of course, you could do this all and keep the color. In fact, you have to for most games because the color is part of the state. And this would just be a 4-way tensor. And you could do the same kinds of things here, but your convolutions would no longer be 2D convolutions, would be 3D convolutions. But like the whole, the approach would be analogous.
I guess his question is like, what do we, instead of stacking these 4 frames together, why don't we just do like recurrent neural network or LSTM? Like, is there any benefit or advantages over that?
Yeah, I see. I mean, you could do that. And then you'd have like a single LSTM, and then you would take, your final hidden state, and you would do something like this. You transform it into, a vector of 4 values and train it in the same way. You could do it. That's true. There's nothing a priori saying like that shouldn't work. The fact that this works without having to add in that recurrent characteristic to the network actually makes this a whole lot simpler to learn. But yeah, you're right. It could, you're both right. Like that's another way to have set up the network to.
Could we shrink the number of states then? Instead of 84 by 84 by 4, it's just 84 by 84 by 1, and then it goes into
no, because like each one of those frames is still part of the state, right? It's like the way to think about that is when you want to compute Q values for actually like playing the game, the model requires you to have all 4 of those frames. So like that defines your state. So I mean, whether you use an LSTM or you do this convolution, the state's still the same. But of course, that's something you can play with, right? You can play with how many frames, so forth.
Yeah, the number of frames is the amount of memory.
Yeah, it's constrained by things like memory, whatever. And of course, like in 2013, 14, 15, our GPUs had a lot less memory. Excuse me. Okay. Other questions? You're good. Great discussion points. Okay, training the Q network. So, the way that you would train this, right, is that you would, the way you would think about this is that you'd like play a bunch of games, right? And then you'd give those games to the network to learn. So there's some problems in that. These kinds of problems persist or exist for all neural networks that do this kind of mini batch sampling, stochastic gradient descent. And that is, if you think about it, if you look at like these groups of 4 frames, for instance, if you're playing one of these simple games like this breakout game, those, if you take, I mean, it's really obvious. We just take like one state and then just move forward, one time step. There's obviously a huge amount of correlation between those 2 states because they're actually sharing 3 of the 4 frames. But even if you move forward, a number of frames, there's still a huge amount of correlation in terms of like those state spaces and like just the state of the game at that point, right? I mean, there's not a whole lot that's changed in just a short amount of time in those games. So what you have, or if you just kind of play these games and then just give it to these neural networks as training data, just directly like that, you have this problem of very inefficient learning, right? Like your mini batches are just made up of like all these examples that are pretty similar to each other. So these gradients that you're computing for these are like very biased, towards like one aspect of how these of the training data, like how these games are played. So your learning is quite slow. It's taking a long time to convert to something useful. So this can lead to even worse, kinds of behaviors like bad feedback loops in terms of like what's being explained here. If these things are biased in a certain way, say that's like biasing you towards moving, like taking an action in a particular direction, now it'll be dominated in that way, and then your game really learns to play poorly in the sense of it's choosing like the most likely action that it's seen in its data because of the bias. So you need to learn you have to add something to the training to overcome this kind of thing. And there's maybe a number of ways you could do this, but one very effective way is known as replay or experience replay. So the way that this works is that it's very simple. As these games are being played, what you keep is you keep a kind of record, sometimes called a replay memory, where you're keeping track of the transitions, like the state, the action taken, the reward given, and then the next state. And you just keep that. You just keep that transition. Okay, and then you can just list all these out. And now what you do when you're training is to randomly sample from just these transitions. Right, so like your mini batches is made up out of sampling IID over all the possible transitions and seen over many games played. What that's going to do is it's going to first of all not be a bunch of transitions that are already temporally correlated. They're going to come from different times in the game or entirely different games, and therefore you get a much better sort of coverage of like possibilities of these state transitions. And so this really improves the efficiency of training and makes it so that your training is a whole lot better. And moreover, the point being made here is that that same transition can show up in many different mini batches, and so that's sort of uniformly spreading the weight out of these examples across many different stochastic updates, and just makes for much better data efficiency. So, like a typical kind of plain vanilla deep Q learning algorithm with this experience replay looks something like this. So, initializing the replay memory, initializing the networks, randomly initializing the parameters. Now, what you would do is you would, play a bunch of these episodes of these games. Go through these full games. Initialize our state. So whatever, like the initial screen pixels are, or whatever at the beginning of the game. And then for these time steps, within each of those learning episodes, we then select a random action, whether if we're exploring, or follow the greedy, or follow the current policy, which would be like a greedy action. This would be different ways of doing exploit or explore. We haven't really talked about that, but it's built into this pseudocode here. We take the action, observe the reward, and get the next state. Store that in our replay memory, and then go back to that experience replay and sample a random mini batch from all those transitions. Oops, sorry. And then compute our loss and update. So in this way, you kind of work through the games. You build up this transition. You start this replay memory. This transition memory, as you build that up, you are able to sample, with more and more like diverse mini batches, and then everything sort of works great, and you've learned this Q value function, this optimal Q value function that you can use to define your optimal policy. So that is, like standard deep Q learning for reinforcement learning in a nutshell. Now, we're going to talk about a couple of other approaches to this that sort of overcome some of the problems in deep Q learning. So what are some of the problems with deep Q learning? Can you think of any? Yeah.
I don't think it works very well with continuous action.
Okay.
Yeah, because
So it doesn't work. Yeah. So what's the problem with continuous action?
if you discretize it, it's gonna create very big output, which we have to make the network like much more complex and takes longer to train.
Okay. Yeah, that's definitely part of it. So like if we have a lot of actions to take, or we have like a lot of states to deal with, this can be a really, really complicated function, right? Like remember, this is a function over the state cross action space, right? So like, if the state space is complicated, like say, these pixel arrangements in these Atari games, but the action space is small, we might have a chance to learn a Q value function. Like in the opposite, if we have like complicated actions with a really simple state space, again, we might be able to do this. But if both are quite complicated, then this can be a really difficult function to learn and to learn well. You might need way more data to be able to kind of generalize well than you can possibly get playing, even a lot of these games. Or, you can think of other kinds of applications of this where this can be quite complicated, right? So like this example where a robot is, grasping some object. This is a really high dimensional state, right? There's the whole, like whatever the environment is, that can be quite complicated. Like all the objects in the environment, the arrangements of those. Not to mention all of the states of like whatever the robotic arm is here, right? So this could be quite a simple arm, maybe just a couple of joints, maybe just like a pincer of some kind. Or this could be like a fully like articulated hand, wrist, elbow, these kind of things. Like this is quite complicated. The state and actions pair. So we shouldn't expect to be able to learn Q value functions very well in that setting, unless we have a whole lot of data that really covers a whole lot of the state and action space. It's not impossible to generate that, but it's really inefficient otherwise. But the policy can actually be quite simple even in these complicated state spaces, right? It's just like, close your hand. Like when just you might everything might be correct for all you need to do is close the hand, or just simple extension of your hand. So what this is getting at is that we might just want to learn the policy directly, right? Not learn this auxiliary Q function to then generate the policy, but just learn the policy directly. So how do we do that? This is an approach known as policy gradients. Okay, so so this time around we're going to have our policies themselves are going to be parameterized. Okay, sort of implicitly. We'll see here as we go, and then we're going to define this J, which is the value of that policy, right? So this J is over the parameters of the policy, and it's again this expected cumulative discounted reward, given the policy. So this is the policy's value, this function J, and it's also a parameterized function, parameterized by the same parameters as the policy. Okay, so simple. We want to find an optimal policy here. Then just means to maximize this value, right? To find parameters theta star that maximize our value. So how do we do this? How do you think we're going to do this? We've been learning how to apply basically one major tool over and over and over again.
We use deep learning.
What's that? Yeah, we use deep learning, but what are we going to do?
So instead of mapping it to Q values, we'll just go back
So where's the neural network going to be?
between the states and the action.
Okay, that's the policy, right? And then what are we going to do to find these optimal parameters?
I haven't thought about it yet.
We're going to do some kind of gradient in this case because we want to maximize ascent, and it's probably going to be stochastic. So yeah, this is the hammer we have. We're going to hit this thing with it and see what comes out. So there's some math to do here. Gradient ascent on the policy parameters. Yep. All right. So what we're going to learn here is something known as the reinforce algorithm, and this is quite popular. This is used a ton. There's a lot of variants of it, but you'll see this a lot in reinforcement learning approaches. Again, because you're directly learning to parameterize the policy and maximize it. So one way to write down this value here is to re-express that expectation as this as the reward over all of these the full trajectory here. So when we typically express this, when we typically express this, we think of this as in these discrete steps here. We take a step, get a reward, take a step, get a reward. Expectation of that over the policy, because the policy could be stochastic. Another way to think about this is is all of those steps being in single trajectories. There's a similar probability distribution, or there's an easy to derive probability distribution that depends on those transition probabilities for the full trajectory. And what we're trying to do is maximize the reward of that full trajectory, given the distribution of trajectories. And we kind of we sort of lazily just write this down as an integral. When I say lazily, it's far more complicated than that. The kind of integral that we actually be doing here, but mathematically we can do this. We kind of know what we need. We're expressing that expectation. We want to get the expected reward given the distribution of trajectories for that trajectory. Sorry, for the distribution of trajectories. Okay. And trajectories look like the following, right? Just as a reminder, right? There are these triples: state action, reward, state action, reward, state action, reward. Okay, so just a little bit of mathematical niceties here.
How do we get the reward? The R.
It is that cumulative reward.
Oh, it's like the score on the.
Yep. Okay, great. So we have this idea. Now what we want to do is we want to differentiate. We want to keep the gradient of this value with respect to these parameters. And this is the thing that we want to maximize. We want to do gradient ascent using this gradient. Well, if certain mathematical properties hold, we can pass this derivative into the integral because we're not integrating over those parameters. We're integrating over the trajectories. So does this help us? In general, this doesn't really help us. Because basically everything is complicated here. Gradients of expectations are just complicated objects in general. We've kind of seen this before when we looked at VAEs. So what does that mean? Well, guess what? We're going to pull some mathematical tricks here. So one thing that we note is that and we saw this again with the VAEs when we were doing some of the manipulations. This gradient here can be written as this gradient of p with respect to the parameter theta can be written as p times the gradient of the log of p. Just given this simple mathematical manipulation, this is just multiplied by 1. This over this is 1. And just noting that this is the gradient of log of p. And so what we do now is we replace that the gradient of p with that expression. Why is that good? Well, it turns out that when we do that, what we are actually doing now, remember, we worked p back into here. And that's good, because now we can write this as an expectation. Like this integral is an expectation, with respect to that distribution p. Again, probabilities of the trajectories. And what's good about that is that whenever we have expectations like this, these things can be actually quite easily estimated using very simple techniques. For instance, Monte Carlo sampling. Basically, randomly sampling trajectories from this distribution, and then this integral is approximated by just computing the average over those samples. And we've seen this a couple of times, throughout the course. So by doing this trick and turning this into an expectation, we can now actually tractably estimate it through some things like these Monte Carlo sampling techniques for integration. Believable so far? Just doing what mathematicians do, just throwing a bunch of math around like it all should work. And if it does work in the end, then you publish the paper. If it doesn't, you never tell anybody about it. All right. So all we're missing here really is having some idea of what this probability distribution is like. And the way that we get at this is by thinking about what this is and rewriting it in the following way. That we have given the parameters theta, we have the associated policy. And remember, the policy is a distribution over our actions given a state. Right? So it's a way of choosing an action given whatever state we're in. And we think of it as a distribution. We sample from that. So it could be deterministic. There's only one, there's only one action that has probability 1, and everything else has zeros, or it could be stochastic, where probability is associated with multiple states, multiple actions. And then, if you remember, think back to what a Markov decision process was. There's another distribution associated with the Markov decision process that tells us, okay, when we have a state and an action, how to get to the next state. And again, this is a distribution over states this time. And again, this could be deterministic. There's only one state you can go to. Many games are like this. But it could also be a distribution over the states given the previous state and the action that we took. So we can write down this distribution over trajectories in this way. The Markov property is being taken into account here by the fact that we're able to factor this over basically all of the states, all of the transitions. We use our policy, whatever state we're in, we use our policy to give us an action. Then we use our Markov transition distribution to give us the next state. So now we have this, somewhat complicated expression for our trajectory distribution, but nevertheless, it's correct. We can take logs of this. Right? This is actually quite simple to do. And now we can take gradients of this. So what's really cool about this, no one brought it up, I didn't really look out and ask questions, but what's really cool about this is there was this distribution right here that we haven't really talked about or explained where it might come from. But notice that when we take we compute the gradient of this expression, there's basically in each of these summands there's two terms, and only one of them depends on the parameters theta. So, and the other one is the transition probability. So this is essentially, this right here is constant with respect to those parameters. So the gradient there is 0, and we only have this term here. And so when we compute the gradient, this collapses to this right here. So we don't have to think about the transition probabilities. It doesn't depend on it at all. So that's nice. We sort of we now have some expression that looks tractable. And now that we've got that, for our expression, let's see, we have it. Oh yeah, up there. Remember, the whole thing we were trying to do from the beginning was to compute the gradient not of log p, but of j. And remember, we wrote j in that way. So our gradient of j now is just this term right here, but with our reward value in there. And so now we actually have a tractable estimate for the gradient of this value that we can work with. And actually, this is actually quite intuitive if you think about it. So remember what we're trying to do here. We're trying to maximize j, over the parameters of our policy. And if you look at this, if it turns out that the reward for a trajectory is high, then what this term is doing is to basically push up the probabilities of the actions that were associated with that trajectory, right? So that's in this, this gradient here, the log of the policy theta. And if the reward is low, then you can push down, or we're not pushing at all. on the probabilities of those actions. So, like in the end, it's quite a simple expression for thinking about like how we're maximizing the value of the policy J. There might be a kind of argument here to make and say that, given this interpretation, we're basically like reinforcing thetas where like all the actions in the trajectory were good. That's not, like in general, that's pretty simplistic, right? Like you can think of like a lot of your favorite games where you really don't have to play like an optimal action at every single time point. There's just like certain time points where that's most important. But like, because it's an expectation, like in general, this actually tends to work. Even though there might be some like bad actions taken along the way, those tend to be kind of wiped out or kind of washed out by the many, the actions that really did produce, a good, like you really could attribute the value of the policy to. So like it tends to work out in practice. And again, like this algorithm, this reinforced algorithm is actually is used quite a bit. Okay, we're gonna adapt this a little bit now to deal with some of the issues. But I'm just going to stop there and just see if there are any questions about this. Any questions? Yeah.
I just have not for policy gradient, but in general, like looking at the Q learning algorithm, it looks like it has to be a episodic task. So if like the task it doesn't have a limited number of episodes. For example, like predicting like stock or something, then how are we gonna deal with like the task or scenario where you don't have like terminal state? I would say.
Like so. I think your comment is something like if there's not like a terminal or end state to the decision process. Like how do you deal with that? Like how does Q learning deal with that?
Yeah.
Because we've kind of moved on from Q learning, let me take that question a little bit later, okay? And just so we don't kind of lose the trajectory, pun not intended here. Questions more just here on the policy gradient. Okay, so I'm just going to assume that it's believable that if we do something like what's done on the right-hand side, if we can express the reward of the trajectory, then for large rewards, we want to increase the probability of actions taken in that trajectory, and if it's low reward, then we don't want to increase those. Okay, so like that intuition sort of makes sense. Now, there's some problems here. We're not going through all the math of it, but this estimator here is actually a very, very high variance estimator for exactly the reasons that I just described. That like assigning credit to the right actions is actually a really hard problem. So like while this can work, we can do some simple things that deal with this problem. Right? It isn't all the action that you take in a trajectory that matter. It's usually just the most important ones. And we sort of wave our hands and say this kind of washes out an expectation. But we can possibly do some things to help here. Can you think about what those might look like? Notice how we're using, like, in this expression here, we're using the full reward, like the reward over the whole trajectory, as like this kind of constant for all of the terms in this series. Right? You could factor it out in some sense.
We want to add some discount factor.
Right. So we want to make sure that we are properly taking into account like discount factors here, given like where we are in the trajectory. That's one way we're going to deal with this. There are some other ways as well. It's a great thought. Let's go through these. So one idea here is the fact that, you can remember that, what I was just saying, we're basically like using that reward in each term of the series, that same reward. But you know, as t increases, you know, we're like looking further and further along in the trajectory. So what might make more sense here is to just use the rewards to just credit, like to credit the action here, to weight the action here, this this gradient of of this policy for this action by the rewards that come after this time step, right? So we shouldn't use any of the rewards before this time step to weight that action, or that gradient of that policy at that action. Just the ones that come after it. That's when it makes sense. That this allows us to give this kind of this like time direction, this kind of autoregressive nature, and then very much in the way that you just described. We want to add back in the discount factor here for each of those time steps for those rewards going forward, so that we're not just this is not just some raw sum, but discounted by how many steps we are in the future. And if you make these kinds of simple adjustments, you start to improve this estimation. Like it reduces the variance of that estimation. Some other problems that arise here. It isn't necessarily. Again, these are other ways to kind of reduce the variance in this estimate. It's not the raw value of the trajectory that's most meaningful, right? What's most important is really is the reward getting better or worse than some kind of like expected or baseline reward. So like in mathematical form, what we mean here is we don't just weight this gradient of the policy for this action by now this adjusted discounted reward, cumulative discounted reward, but we compare it to some sort of like baseline value, baseline reward that we should like expect to be the case for that state. Now all of a sudden we have a function of state again. That should remind us of something. Oh yeah, sorry. I'm skipping ahead too fast. How do we choose this baseline? So the simplest baseline here is just the cost. Well, there are many simple baselines. A sensible one is this moving average of rewards experienced so far from all the trajectories. So if what we're doing is as we're looking at trajectories, we're keeping a kind of average of those. That's sort of like, you can think of it as some kind of like samples from the distribution of trajectories, and the average there should represent what we should expect on average. So if we compute that and let that be our b, then that's a sensible baseline to choose. And if we do use that, then what we have is like what's truly known as the plain vanilla reinforced algorithm. So it looks like that, where this baseline right here is chosen to be the average of trajectories, average reward of trajectories that we've seen so far. Now, we can do a lot better with these baselines. So, better baselines. We want to push up the probability of an action from a state if this action was better than the expected value of what we should get from that state. What does this remind you of? We've already actually defined a function to give you the expected value of a state. What function was that?
Value.
Yeah, exactly. It was the value function. And so, intuitively, what we're thinking here is we're happy with an action A in a state S if the Q value function at that state in action is higher than the value function at that state, right? What that means is that the action is like, if it's larger, then it's preferred. If it's smaller, then it's not preferred. It's not doing better than expected. So, another way to think about this estimate, we did all this work to get away from Q value and V value functions, Q value and just value functions. But we've all of a sudden decided that it might work to put these back in here as a way of properly weighting our estimates of the terms in our estimate of the gradient of this value function for our policy. Why is this any good? Well, it turns out that we get now another class of reinforcement learning algorithms. So by doing this, we get another class of algorithms known as actor-critic algorithms. So obviously we don't know the Q and V functions, but can we learn them? And the answer is yes, we can actually combine policy gradients and Q learning by training an actor and a critic. So the actor, is our policy, and this critic is our Q value function. What's happening here is you have an actor that's deciding which action to take, and the critic, the V value function, is telling you through this expression right here, what's known as this advantage function, it's telling you how good of an action that actually was. And if you did take a bad action, it's giving you some weight by which you should adjust, your policy. This has some advantages. You don't have to learn, actually, this is quite interesting, and this is what makes this combination actually work well together. For these Q value functions, we are to learn an optimal policy, we don't actually have to learn the full Q value function. We only need to learn the Q value function for the state and action pairs that are generated by the policy. So we actually overcome this issue that we had with just doing straight, deep Q learning by incorporating in this way, because now all we need is to have learned it for just those states and actions that are generated by our policy. So that could dramatically reduce the state action pair space that we actually need to learn the Q value function for. What's cool about this too is that there are some of those useful tricks like experience replay from Q learning and other ones that we haven't talked about can be incorporated to learn this. And when we're all said and done, we actually have this advantage function, which we can use to understand the values of actions. And so we get an actor-critic algorithm that looks like the following. Oh, sorry. We run over iterations. We sample trajectories under the current policy. This is initializing our gradient step for the parameters. We run over episodes and transitions in that episode, and we compute our current estimate of our advantage function. And then we take a gradient step with respect to the parameters of our policy, and then we use that to update the parameters of our value function, and we update them all, and we run this through all the for loops. So pretty simple algorithm, but in the end quite powerful for learning optimal policies that incorporates the very things that we were trying to avoid when we created policy ingredients. Again, this is not necessary. It turns out that the reinforced algorithm is very often used, but you'll also see after-critic algorithms for different reasons, for different reinforcement learning problems.
It almost seems like a GAN, like a generative.
Yeah, it's very much like that. There's not really an adversary here, so it's different in that way. But what you are using is you're using a different model of value, and doing this kind of iterative training to allow you to learn this policy. So it's similar in the sense that there's two models and they reinforce each other, but they act together towards the same goal rather than adversarial.
Could we replace the critic with an adversary, or maybe?
I mean, off the top of my head, there might be some clever thing that could be done there, but remember, an adversary would be problematic here, right? Because, let's see. The way that adversaries come into reinforcement learning in these settings is when you're in a kind of game where there are multiple agents and their reward functions are adversarial to each other, right? So one agent's reward ends up being positive reward is the other agent's negative reward, right? This is two-player games, multi-agent games. This is often the case. So that kind of concept arises.
So GANs came from adversarial search, right? So is there anyone coming up with something like an active critic that goes into a GCN or something, a generative critic model, a network?
I don't know. And GANs didn't come from adversarial search. I mean, GANs came from the desire to be able to transform one distribution into another. That's literally where they came from. And
I meant the idea when I can't quite remember when he wrote the paper originally. He was taking a course from AI, and he was doing adversarial search. That's where he came up with that.
I am almost certain that's wrong, but we could talk about it a little bit later. But yeah, the apocryphal story is that Ian Goodfellow and others are sitting in a bar trying to figure out how you would use neural networks to turn one distribution into another, and came up with this adversarial way of doing it. But you know what? I don't know. This isn't exact history. Okay, so cool. What's an example here of reinforce? Well, I mean, gosh, there's so many things we could look at. Here's kind of a weird example that combines a lot of things that we've done in this class so far, and that is this idea of trying to kind of recreate what our eyes do when we take in an image. So convolutional networks in general are looking at the whole image basically at once, and aggregating, accumulating, condensing information there to decide something about what's going on in the image. But really, if you study the physiology of vision, and you can just do this experiment yourself right now, although as soon as you're aware of it, you stop doing it. It's one of those weird things. But when you take in a scene, you don't look at one spot. You actually rapidly look at a variety of spots. They're called saccades, and your eyes are going to move, And it's a way of like, thought as a way to quickly integrating a lot of information about the scene, and there's some thought to around like that we're actually even capable of learning because we don't have static vision, but we move the point of view of our eyes around quite a bit. So we want to be able to kind of do the same sort of thing here, and so what we want to do is we want to kind of simulate this idea of like a sequence of glimpses of an image to make a decision. So the simple setting here that we're going to look at is MNIST, although it's an adjusted MNIST where the image, the actual figure, the digit itself, is going to be not just in the center view, but it could be kind of anywhere in a larger view. And we're only going to let the network look at a very small portion of the image. Okay? So so a glimpse is like kind of randomly selecting some small subset of pixels to look at. And what we want the agent to learn to do is given that glimpse, to like then make a decision about where to look next, and where to like to adjust the glimpse view, and to do that a couple of different times to ultimately like correctly classify the digit. Okay? So in terms of our reinforcement learning setup, the state is going to be glimpses that we've seen so far, right? So we'll do one, and then we're going to take an action and we'll do another. So the state kind of accumulates in that way. And then the action is basically which XY coordinates are we going to focus on? We're going to be the center of that view there next. And our reward is a 1 if at the final time step we classify the image correctly and a 0 otherwise. So what we're going to try to do is use basically like the pixels that we glimpse to then inform us on like where we ought to look next given like this limited view, and do that in a few steps so that picking a fixed number of glimpses we can take, we correctly classify. So like you're trying to maximize the information you take in at each one of these glimpses to do this task well. The trouble here in like maybe setting this up in other ways is that this operation of glimpsing is non-differentiable. You can't differentiate the movement of a glimpse. But we can learn a policy for taking glimpse using the reinforced algorithm, and therefore like learn to do this task. So this is a really interesting example because approaching this not as a supervised task but as a reinforcement learning task actually allows us to learn the task. And that's kind of a cool thing. So the way this is set up is to have a recurrent neural network that's going to basically accumulate the evidence from the different glimpses that we're going to take. And learn our policy from whatever state that we're in to choose the next set of the next coordinates for our glimpse. So the example you're trying to see here is something like, at first it kind of randomly chooses something. Actually, it could learn to choose, if there's some bias in where like white pixels might be in this image, it might learn to do that. But if this is like appropriately randomly generated these images, then we shouldn't have a problem. But anyways, it looks and it sees, hey, nothing here. And now let's take another look. It's learned to like, from wherever it started, where's the most likely place to find some pixels. So it'll do that. It'll get the next state. It'll use that glimpse to then generate where it should go next. This is actually looking at the trajectory of like a train network. So now it's moved itself, not this huge jump from where it was before, but up, up and to the left here. You can imagine like why it might have learned to do that because the the non-black pixels right here are here in the upper left. So it's most likely that there are more of these non-black pixels up and to the left. So it learned to do that. It then generates another glimpse. Again, it's like given this state, it's learned to maybe look down and to the left here. And you can imagine why it might have done that, right? Because given this pixel arrangement, there's like some ambiguity of whether this is a 2 or a 6 or things like that. And so it can disambiguate itself by looking down and to the left. It does that. It then makes a decision from there where to go next, take a glimpse, and then finally, it'll make a prediction. And if we fix 5 glimpses to be the maximum number of glimpses you can take, then this thing learns to choose where to take the next glimpse given the previous glimpses, and using the reinforcement algorithm, the reinforce algorithm. And then all this is supervised. The RNN part of this is supervised by the classification tests. So it's a really cool combination of convolutional networks for processing the glimpses, reinforcement learning for producing the next glimpse, and then the RNN for accumulating the evidence over all of the glimpses and producing a classification prediction. And these kinds of things have been used a whole bunch of, there's been in other ways. But anyway, it's just kind of a cool example where it combines a lot of the things that we've learned in this class. I can see that our time's up. I'm just going to quickly say that policy gradients are quite powerful. AlphaGo 0, AlphaZero, all these iterations of reinforcement learning agents that learn to play Go and play, beating the world champion at Go at the time, being the world champion. So doing that with all these built-in rules, doing this again, but no longer playing using human play, but playing against itself, and then a little bit later. This shows just chess and shows you, but for Go as well, without even having built in the rules of the game, it builds a model of the world. These are all done with policy gradients and a whole lot of other clever engineering. But again, just policy gradients and reinforce being at the core of these algorithms. One really fun thing to do to get into this area some more is to go and play around with OpenAI Gym, which is a bunch of code and environments for playing the Atari Games and playing a whole lot of other kinds of games, and having a bunch of code with a lot of these reinforcement algorithms, make it available. You can really learn quite a bit about how these things work. It's really a fascinating and cool resource. And that's it. Policy gradients, very general, maybe have this high variance problem that we learned we're going to deal with through the active critic models. Q learning doesn't always work, but it can be more efficient if you do this kind of this exploration replay. There's never really any guarantees, but policy gradients, they're trying to converge to a local maximum of your value of the policy. And this is often quite good. In Q learning, there really are no guarantees since you're approximating Bellman equations with a complicated function approximator. So why you even do those over policy gradients, who knows? But it's still there.